In this video I want to explain the really important concept of the differential of a vector, something that you can write dv, or if I was handwriting it would be dv, remember the arrow, okay? So this is something that you can actually use without it being as part of a differentiation, dv dt, but actually you can work with dv as a separate entity, okay? Similar to what you could do in one dimension. So to explain this, in fact, I'm going to start with one dimension, okay? But I'm going to use this analogy of a function as an input slider and an output slider, okay? So remember, a function in one dimension is this function f of x, which depends on x. And this means that for each value of x, you get an output value, right? So if you make a list of all the values, you end up having a curve as you are used to, okay? But it's nothing else than saying that for each value of x, you get an output value f of x, okay? So in some sense, you could plot this as a machine. Imagine an actual mechanical machine in which you have a slider, which is x, which you can change. And for each value of x, you get a value of f, okay? And that's what I'm saying here. So let me actually show that to you. I have built this machine in Mathematica, okay? So I have a slider here, and when I change my slider, you can see that the output slider automatically changes, okay? So different values of x, which are here written on the left, are associated to different values of f of x, okay? And notice something. Sometimes when I move my slider of x, the slider of f of x changes very little. Notice that only the last decimals are changing, yeah? So I'm changing x quite a bit, but f of x is changing very little. However, at some other points, it's just the opposite. When I change x by very little, like I'm doing now, f of x changes by a lot, okay? And even it can have opposite signs. So for example, right here, so now if I move x up, f of x moves down. And if I move x down, f of x moves up. So the change in f of x has an opposite sign to the change of x, okay? So that is actually what the derivative means. So think about it. The ratio between the change in f of x divided by the change of x is exactly what the derivative measures. So the ratio, how much this changes, divided by how much this changes. And it can be a small number when the change in f of x is small. It can be a big number when the change of f of x is big. It can be negative if the change of f of x is opposite to the change of x. And this is all intuitive by thinking about these sliders. And of course it matches with what you knew about the derivative being the slope of the function f of x. How much is f of x changing when you change x, okay? So consider this. We have a certain value of x, and this certain value of x produces a value of f. Now if we increase x by an amount dx, then the value of f increases by an amount df, okay? And this is what I'm writing here. And the key concept of defining a derivative, df over dx, is that this df divided by dx becomes constant when dx is very small. In other words, df at some point becomes proportional to dx. So as long as dx is very small, if I move dx by a little bit, df will move by another little bit. If dx I move it by twice as much, df will move by twice as much. This is always true as long as the movement is very small, which is equivalent to saying that we are zooming in so much into the function that it becomes a straight line eventually. Yeah. So the change in f becomes proportional to the change in x, okay? So that's a way of thinking about derivatives in one dimension. But the nice thing of this picture of the sliders is that it's very easy to turn into the case of vectors, as I have done here, okay? So in the case of vectors, a vector v that depends on one variable, we can imagine that we have one slider in the input, but then we have all of these sliders, which are all of the different components of vector v. And I have built this machine in Mathematica. here you can see it. So now I have a slider for my input, which in this case I called it x, and then I have 3 sliders on the output, which are the 3 components f1, f2, f3 of a vector, which could be the vector f. Okay, and now note that when I move x, the 3 sliders change, but in general they change in different ways, right? They are independent sliders, so each slider is a function of x, but it's a different function. Okay, so now you may say, okay, when I change x by a small amount, like I'm doing now, f1 is changing by a small amount, f2 is almost not changing at all, and f3 is changing by a very big amount and in the opposite direction. So this means that the derivative of this vector f has a first component that is positive and small, it has a second component that is very close to 0, and it has a third component that is big and negative. Okay, so that's how you could interpret the derivative of vector f with respect to x. And now we can think about the differential dx, which is the amount by which I increase x, and the differential df vector, which would be creating a vector with the 3 differentials of the 3 output sliders. So going back to our whiteboard, now I'm using u as the input variable and v1, v2, vm as the output variable, as the output vector. So by changing u by an amount du, we see that each slider changes by a different amount, and we can actually collect all of these dv1, dv2, and dvm. We could collect it into a vector, okay? And this would be our vector dv is equal to dv1, dv2, up to dvm. Okay, so this vector dv represents this differential vector. Okay, and it only works in the limit when du goes to 0. Okay, so these values are all in the limit going to 0, but nevertheless it's very useful to work with dv's. Okay, for example, imagine the example I gave you earlier of the position vector r changing as a function of t. Okay, so this is a position vector. So what would dr be equal to? So dr is by how much r changes when we change t by an amount dt. Okay, and the one way you can find it is by using this chain rule. This is dr over dt multiplied by dt. Okay, so how much does r change when I change dt multiplied by how much I changed dt, and this gives you dr. Okay, but one way of writing this is that this is equal to the velocity times dt, because dr divided by dt is equal to a vector, which is the velocity. Okay, so you could say that dr, the differential displacement, is equal to the velocity times the differential of time, so v dt. And it's very useful to work with this. For example, now you can say that r, the total r vector, is an integral of the differentials of r. And if you substitute dr here, you get this is the integral of v dt, which is an equation that we already knew from classical mechanics. Yeah, but now it makes sense that it's simply doing the integration of a differential dr. Okay, and the same way that when you do the differential of dx, the answer is just x. Yeah, on the limits 0 to x. Then also the integration of the differential dr is equal to the vector r when we change the parameter from t equals 0 to t equals capital T, for example. Yeah. So that will give us the total displacement between time 0 and time t. So it's very useful to work with differential of vectors like dr. If we go back to when I explained the differentiation of vectors, and I mentioned that you are just adding these infinitesimal arrows, yeah? So each of these little arrows in the limit when they are going to 0, these are equal to dr, which is v of t times dt. It's each of these little arrows, okay? Excellent. So thanks for watching and see you in the next video.